Hey guys, welcome to the second section of the Fluid Mechanics mini course. In this section, we will be covering fluid dynamics or moving fluids. Now we are going to focus specifically on fluids that are considered simplified ideal fluids. That means that they're non-viscous. In other words, we will ignore the internal resistance or friction that the fluid particles have along one another. We're also going to say that all these fluids are incompressible, which we've done before in the previous section. We are even going to consider gases to be incompressible. Now, the reason that incompressibility would be important to focus on in this first part of the Fluid Mechanics mini course is because we want density to remain constant. We don't want the density to be a function. In order to do focus and calculations where the density is changing and the fluid is compressible, we would need to use calculus. And this is just an intro course that is focusing more so on the conceptual understanding and the algebraic relationships rather than on applying calculus. So before we continue in this video, I highly recommend going to the fet.colorado.edu website and taking a look at their very cool simulation called Fluid Pressure and Flow. And what I want you to try to do is figure out what happens, how could you define or sort of describe the flow rate of the fluid? In addition, how can you describe the fluid flow rate when the diameter of the tube or the pipe that it's flowing through changes? Don't worry about looking at anything else in terms of pressure or anything like that right now. We'll get to that later, but I highly recommend going and trying that simulation first before continuing with this video. All right, so the first question we're going to consider is what will cause a fluid to flow from what we already have discussed. So I suggest you pause the video and figure out what would cause the fluid to flow or move from one place to another versus stay at rest. Hopefully, what you thought was if there's a pressure difference in the fluid, then there will be fluid flow. Very good. Now, if you consider that a source of fluid flow might be some sort of mechanism that pushes the fluid, then we could also establish a fluid flow from that perspective as well. But most of the time, what we're going to focus on is the difference in pressure being the reason for the fluid flow. Now, in order to discuss fluid flow, we have to come up with a way to measure it or describe it. And we're going to use this term flow rate. So instead of looking at the individual speed of the particles, we're going to look at an overall flow rate of the fluid. Now, if you've studied electricity and circuits, we've talked about the flow rate similarly to the current, where we're focusing more so on the amount of fluid or the amount of charge passing a certain point in a wire, or in this case in a pipe, in a given amount of time. So once again, pause the video and try to figure out an expression for flow rate. How would you mathematically describe flow rate? Hopefully you were able to write the amount of volume of a fluid per unit of time. And in physics, most of the time, we use the letter uppercase Q to represent flow rate, just to keep it interesting. So let's consider this straight section of pipe, all right? And this is going to be a pipe filled with water, and we're not going to be concerned with what's happening on either other sides of the pipe, but we just know that this fluid is flowing through the pipe. Now, if we select this location 1 over here on the left and location 2 over here on the right, we can state that the flow rate is the same throughout this pipe if the water is incompressible and non-viscous. So in other words, the volume of fluid passing this point right here has to be the same as the volume of fluid passing this point right here in a given amount of time. And we already discussed this before in a sense by looking at it in the hydraulic systems, in that we were saying that the fluid has to obey the idea of conservation of mass or conservation of matter. So in other words, if say 5 liters of fluid passes this point in a second, if this is an incompressible fluid, 5 liters also has to pass this point. We can't say that now only 4 liters is passing this point, because then that would mean that there's a buildup of fluid somewhere else, or a place where the fluid is escaping the system. And we are considering that this is a closed system. So the fluid amount should be the same. Now, I'm going to try to figure out if I can write an expression for the speed of the fluid, or incorporate something about the speed rather than just focusing on the flow rate. And it turns out that I can. If I write volume as area, which would be this cross-sectional area, times the delta x, if you want to call it that. Now, usually we would say area times height, but because I have this laying on its side, it's not really the height per se, but this horizontal distance. So if I take volume to equal area times height, or delta x, and I say that that volume per unit of time, and I write it this way, then I can see here very interestingly that delta x over t would be an average velocity, right? And so we could also write flow rate as area times velocity. And then we could extrapolate that to say that if the flow rate is the same in this portion of pipe as it is in this other portion of pipe, then I should actually show that if the cross-sectional areas are the same, then the velocity should be the same. So we have the same average velocity between both portions of this pipe because the area is the same. Now let's take a look at a really cool, I would say, phenomenon that we've all probably experienced if we played with like a garden hose, or even a shower head that you can change settings on. We notice that there's ways to make the water appear, at least, to come out faster from the opening. All right, so if we take a look over here, I have 3 different hose heads that you could attach to your garden hose. And I'm really going to focus here on the middle one. Now you can see the attachment that's here on the bottom of this image. That's a wider diameter than the very top of the nozzle, which is a very small diameter area, cross-sectional area. So if we take our flow rate equation again, and we know that the same amount of water that's passing through, say, this point on the hose has to be the same volume of water that's exiting the hose per second, right? Because we're saying that the water can't get used up anywhere or invented anywhere. In other words, that we have to establish conservation of matter. That if the area is different, all right, so if we set the flow rate over here equal to the flow rate over here, the area being different, so we have a large area on this part and a small area on this part, means that the speeds will have to be different in order to maintain conservation of matter and to keep this as an equality. So where would it be faster? Well, the spot where the area is smaller, in order to stay the same flow rate, it will actually have to be faster. So it does, in fact, doesn't only appear to be moving faster, it is actually moving faster. So when the diameter of the tube changes, the water moves faster. All right, so here we have a picture of an apartment that has exposed ductwork. And this has become, a very popular kind of industrial style in exposing the ductwork. But it's also really cool, not only how it looks, but also for us to be able to see and analyze how the ductwork actually works. So if we take a look over here, you can see that the diameter of this air duct is actually becoming smaller as it kind of terminates at the end of this opening. Now, if you think about that, what we've just shown is that when the area, the cross-sectional area of the tube decreases, the velocity of whatever's flowing through it will actually increase. So when the area decreases towards the end, we actually have a higher velocity and the air comes out kind of moving faster. Now, at this point, I really recommend going back to the little simulation lab that you were presented originally, and I want you to try to figure out, why is it that the air gets kind of pulled or pushed out more towards the ends of these ducts? Now, we know that it is moving faster, yes, but that doesn't tell us exactly why it's moving faster, right? Or what's causing it to flow in this direction. So go back to the PhET simulation and try to figure that out, then come back for the next video where I will discuss how this actually works.